We now continue with our discussion of properties of the real number system. So far, we've established that both addition and multiplication are commutative and they are also associative. Now we're going to look at a property that involves two operations. It is called the distributive property of multiplication over addition, often just referred to as the distributive property. However, it's one of many distributive properties, so it's technically the distributive property of multiplication over addition. It's a very important property in computations, as you will soon see. So let's first start with an example, see if we can make sense of it, and then we'll get to the standard computations involving the distributive property. So here's a scenario. A dad wants to buy his 3 kids soccer uniforms. Let's say a uniform consists of an $11 jersey, a $9 pair of shorts, $12 shin guards, and $19 cleats. Each uniform has those 4 things in it. Let's look at these two scenarios and see if there's a difference in how much money the dad would pay. So in scenario A, he buys all 3 jerseys on one day, then all 3 shorts a second day, then all 3 shin guards a third day, and all 3 pairs of cleats a fourth day. Would that be a different total amount from if he bought all 3 uniforms at once? Think about that for a moment. We would like to actually write down an expression for each of these scenarios that would represent the total amount of money he needs to spend. In scenario A, he buys all 3 jerseys one day, so he's going to have to pay $11 3 times, so 3 times 11. And then on the second day, he's going to have to pay more money, so we're going to add on, he's going to buy 3 shorts, and the shorts are each $9, so he's going to have to pay 3 times $9. Plus on the third day, he's going to have to buy 3 shin guards each at $12 a piece. And then on the fourth day, he's going to have to buy 3 cleats, each at $19 a piece. So the first day he pays $33, the second day he pays $27, the third day he pays $36, and the fourth day he spends $57 for a total of $153. Let's look in scenario B. In scenario B, he'd buy all 3 uniforms at once. Well, the price of one uniform is $11 plus $9 for the shorts, plus $12 for the shin guards, plus $19 for the cleats. And he's got to get 3 of those. So if we do this computation, each uniform costs the sum of these 4 numbers added together. And we get 51. And then of course he needs to buy 3 of those uniforms. 3 times 51 gives us a total of $153. So the answer is, it doesn't matter whether he buys it this way or this way. It's going to be the same amount of money, $153. Let's look at these two computations more closely on the next screen. In scenario A, we had this computation. In scenario B, we had this computation. And we saw that they were both 153. So this was equal to this expression. Notice that that's essentially the same thing as doing the 3 times the 11, gives us this piece here, doing the 3 times the 9, which gives us this piece here, the 3 times the 12, which gives us this piece here, and the 3 times the 19, which gives us this piece here. And notice these were all added together, so these are still all added together. This distributing of the 3 into this sum is exactly what we're talking about, the distributive property of multiplication over addition. 3 times the sum, the 3 can multiply in with each part of the sum. The generalized form of this is if you've got A times a sum or technically a difference, you can distribute the A into the B and into the C, and you'd have AB plus AC if you had the addition here, or AB minus AC if you had the subtraction here. Let's now use the distributive property to rewrite each of these expressions. Up here, you technically wouldn't need to multiply the 3 in here because you can add these together. But we wanted to see that these two things are actually the same. Now I can't actually combine the x and the 2, so what we want to do is to rewrite this without these parentheses here, i.e. we need to distribute the 5 into the x plus 2 because we're multiplying the sum by the number 5. And when you do that, 5 times x gives us 5x, and then plus, because this was addition here, 5 times 2 is 10. 5 times the quantity x plus 2 is the same thing as 5x plus 10. Let's take a look at the next one. Negative 7 times 3 is negative 21, plus Negative 7 times x is negative 7x. This is 100% correct here, like this. Very often, though, some people won't want to write plus negative 7x and may rewrite this as just minus positive 7x, which we saw earlier is the same thing. So if you write this or this, they're exactly the same thing. Let's continue. Negative 2 distributed into the negative 2x is positive 4x, because negative 2 times negative 2x is 4x, minus negative 2 times the 1 is negative 2. And people typically would not write subtracting a negative. Recall from your past that subtracting a negative is also the same thing as adding a positive. So this is the same thing as plus positive 2. More often than not, you would see it written like this rather than this. So this expression is the same thing as just 4x plus 2. And then finally, you might look at this one and say, well, what are we distributing? There's no number out here. I just see this sign. Well, first thing, let's recall that the opposite of x, this is technically the opposite of this difference of x and 4, is the same thing as negative 1 times the x. So this expression is the same thing as negative 1 times the x minus 4. So what we're really doing here is we're distributing in a negative 1. Negative 1 times x, you can write down negative 1 times x, or technically negative 1 times x, as you see up here, is the opposite of x. So this is the opposite of x. Then we have minus negative 1 times 4 is negative 4. And again, people would not typically write minus negative 4. So this can be rewritten as negative x plus positive 4. So 5x plus 10 is the same thing as this. Negative 21 minus 7x is the same thing as this. 4x plus 2 is the same thing as this. And the opposite of x plus 4 is the same thing as this. We ultimately want to be able to use the commutative, associative, and distributive properties to clean up expressions in general. To do that, we need to first define a few things. First is the idea of a coefficient. The coefficient of a term, and again, a term is the parts being added together, is the numeric factor of the term. So what are the coefficients of each of the variable expressions in this right here? This is not a variable expression, so we wouldn't be worrying about that, but this and this are. So the coefficient of the opposite of x squared, remember the opposite of x squared is negative 1 times x squared. So the coefficient is negative 1. 7x has a coefficient of just 7. Negative 1 is the coefficient of this term, and 7 is the coefficient of this term. We needed to define coefficient in order to be able to combine what we call like terms. Now, real quick, you can multiply and divide any types of terms. They do not need to be what are called like terms, but to add or subtract terms, they do need to be like terms. So we need to define like terms because when we add or subtract like terms, the coefficients play a key role in that process. First, like terms are terms with the same exact variable factors, including exponents. So this is a term right here, 8x squared y. We want to write down a term that is a like term to 8x squared y. And it has to have the same exact variable factors, including the exponents on those factors. So technically, 5x squared y would be an example of a like term because the variable part along with the exponent is exactly the same. Or negative 8x squared y. That is a like term. Or 42.7 x squared y. These are all like terms because they have the exact same variable part, including the exponents on those variables. Now that we have like terms defined, we can now talk about how we add and subtract like terms. And we add and subtract like terms directly as a function of the distributive property. What you do is you simply add or subtract the coefficients of the terms and you keep the variable part exactly the same. So we want to combine the like terms here. We've got negative 3x plus 10x. These are like terms because this variable factor of this term is x, and the variable factor of this term is also just x. So negative 3x plus 10x, you, in this case, add the coefficients, negative 3 plus 10, which gives us 7. And then the variable part stays exactly the same. So it's simply just 7x. And the reason, again, this is true is because of the distributive property. If you had x times negative 3 plus 10, that quantity, you distribute the x in here, which would give you the negative 3x plus the 10x. And of course, negative 3 plus 10 is just 7. So this thing and this thing must be exactly the same. So to add like terms, you simply add the coefficients and keep the variable part the same. Same deal here. To do 5x squared minus 17x squared, we simply subtract the coefficients. 5 minus 17 gives us negative 12. So we have negative 12, and the variable part stays the same, is x squared, not x to the fourth, for example. The only time the variable part would change, the exponents on it, is up here in this scenario. So the variable part and its exponents may only change if you are multiplying or dividing terms. Again, we are adding and subtracting like terms, so the variable with the exponent part will not change. Let's try this one. If you've got 8x squared y minus 5x squared y plus 7x squared y, we've got like terms. 8x squared y minus 5x squared y would give us 3x squared y, because 8 minus 5 is 3. And then 3x squared y plus 7x squared y would give us a total of 10x squared y. Again, the variable part does not change. Simply combine the coefficients accordingly.